Hello students, and welcome to the video lecture covering section 10.2, areas of trapezoids, rhombuses, and kites. Our learning goal is to be able to find the area of a trapezoid, a rhombus, or a kite. So first we have the formula for the area of a wait a second, no, we already covered parallelograms. We need the formula for area of a trapezoid. Oh, so there it is. So the area of a trapezoid is given by 1/2 the height times the sum of the two bases. So why is it that I have the formula for area of a parallelogram here? So let's start with a trapezoid. And let's take part of that trapezoid and just cut it right off the top. So let's draw a line that connects the midpoint to the midpoint. And let's take this part of the trapezoid and let's just chop it right off there and flip it over. So you can see what I've done here is I've taken this part of the trapezoid and I've taken it off and I've flipped it over onto its top. Now, if you look at the new parallelogram created by those two pieces of the trapezoid, you can see that the base of this parallelogram, or the entire length along the bottom of this parallelogram, is B1 plus B2 from the original trapezoid. And the height of this new parallelogram, we'll call that H, is exactly half of the height of this original trapezoid. We'll call that H2. So in this case, we've created a new parallelogram whose base is the sum of the two bases of the trapezoids, and the height is actually half of the original height of the trapezoid. So hopefully it makes sense where the formula for area of a trapezoid comes from. So in this case, we say that the height of the trapezoid is the perpendicular distance between the two bases. So let's take a look at a few examples. First, let's try to find the approximate area of the state of Nevada. Since Nevada is approximately a trapezoid, we can use the formula for area of a trapezoid. So we have here that the area is going to be 1/2 the height times the sum of the two bases B1 plus B2. Now in this picture, the state of Nevada is actually not an ideal trapezoid because we like to see the bases so that they're parallel. However, we can just plug into the formula as long as we're careful. So here we have that the area is 1/2 the height, which is 309 miles, times the sum of the two bases, or 205, plus 511. So the first thing that I would do here is 1/2 times 309. And I would take 205 plus 511 in the parentheses and get 716. I would multiply the 309 times half of 716, which is 358. And I would say that the approximate area of the state of Nevada, in this case, is about 110,622 square miles. So let's try another example. So what is the area of a trapezoid with height 7 centimeters and bases of 12 and 15? Since we don't have a picture here, probably a good idea to include one. So we have bases that are 12 and 15, and the height, or the perpendicular distance between those two bases, is 7 centimeters. So in this case, our formula, area is going to equal 1/2 the height, or 7, times the sum of the two bases, 12 plus 15. 12 plus 15 is 27, so we have 1/2 of 7 times 27, which is equal to 1/2 of 189. And so this is going to be 94.5 square centimeters. So here, problem 2 is finding the area using a right triangle. So it says, what is the area of trapezoid PQRS? We know our formula is area equals 1/2 the height times the sum of the two bases. The only problem is, in this particular example, we're not given the height, so we have to find that. So what we need to do is draw the height in. And if you notice here we have a right triangle. So let's go ahead and look at that triangle individually. We know that one of the angles is a 60-degree angle. We know that this bottom angle is a right angle, since this is the height of the trapezoid. So we know that this is a 30, 60, 90 right triangle. So we need to find the difference between the top and the bottom. So since this is a rectangle, SRQ, and then we can call this A, since SRQA is a rectangle, we know that this is 5, and the short side down here is going to have to be 2. And so remember, the side opposite the 60-degree angle is going to be 2 times the square root of 3. And so now we know the height of this trapezoid. So we know that this is 1/2. The height is 2 times the square root of 3. And the sum of the bases is 5 plus 7. The 1/2 and the 2 cancel. We get 5 plus 7, which is 12, times the square root of 3. And area is always in units squared, so this is meters squared. If the question wanted a rough approximation, we'd say that this is about 20.78 square meters. Theorem 10.5 tells us that the area of a rhombus or a kite is 1/2 the length of D1 times D2, where D1 and D2 represent the lengths of diagonals. So let's go ahead and take a look at a couple examples. So the only thing that we need to find the area of a kite is the length of the two diagonals. So here we need to know the length of Ln, and we need to know the length of Km. Ln has two parts which are both 3 meters. So the length of Ln is going to be 6 meters. The length of Km is 2 parts. One part's 2, the other part's 5, so that has a length of 7 meters. So the area in this case is 1/2 D1 times D2. And so we get 1/2 of diagonal 1, which is 6, times diagonal 2, which is 7. Half of 6 is 3, and 3 times 7 is 21 meters squared. So this second example doesn't have a picture, but we can solve it anyways. We know that the formula for area of a kite is 1/2 diagonal 1 times diagonal 2. The diagonals are given in the question, 9 inches and 12 inches. So we just go ahead and plug those into the formula. We have 1/2, diagonal 1 is 12, diagonal 2 is 9. The 1/2 and the 12, we can combine those to be a 6. And 6 times 9 is 54 square inches. And so we have our final problem of the day. The high occupancy vehicle lane is marked by a series of diamonds or rhombuses painted on the pavement. What is the area of the HOV line diamond shown at the right? So again, we need to know the lengths of the diagonals. But here we have a small problem, because what they've given us is the length of the hypotenuse and the length of one of the legs. So we need to use those two pieces of information to find the length of the other leg of this triangle, triangle ABC. So let's go ahead and draw a picture of ABC. So we know that the hypotenuse is 6.5, and the shorter of the two legs is 2.5. So here we know that if we want to call this the length of AB, we know that AB squared plus 2.5 squared has to equal 6.5 squared. So then AB squared is going to have to equal 6.5 squared minus 2.5 squared. And so AB is going to have to equal the square root of 6.5 squared minus 2.5 squared. And so by plugging this into the calculator, we find that the length of segment AB is 6 feet. So now we can find the length of diagonal 1. It's 2 parts of 6, which is 12 feet. We can find the length of diagonal 2, which is 2 parts of 2.5, or 5. And so the area of this figure is going to equal 1/2 diagonal 1, which is 12, times diagonal 2, which is 5. Half of 12 is 6, and 6 times 5 is going to be 30 units, or 30 square feet. And that concludes this lesson on section 10.2, area of trapezoids, rhombuses, and kites. Thanks for your attention, and I'll see you soon.